Understanding sklearn's PolynomialCountSketch kernel approximation. The PolynomialCountSketch class in sklearn implements an approximate feature mapping technique for nonlinear kernel methods, specifically for polynomial kernels. It allows you to efficiently approximate the effect of a high-dimensional feature space produced by a polynomial kernel without explicitly computing the kernel itself. Let's break down the key aspects of this technique and its implementation in sklearn. 1. The challenge of high-dimensional kernels. Polynomial kernels are powerful tools in machine learning. They introduce non-linearity by creating new features that are combinations of the original features. This can be very effective for capturing complex relationships within your data. The problem explicitly calculating the polynomial kernel can be computationally expensive and memory-intensive, especially when dealing with high-dimensional datasets or high-degree polynomials. 2. Kernel approximation to the rescue. Kernel approximation methods aim to approximate the effect of the kernel without the need for explicit computation. This significantly reduces computational cost and memory requirements. PolynomialCountSketch. This particular method focuses on approximating polynomial kernels. It achieves this by using a technique called CountSketch, which essentially hashes the original features into a lower dimensional space while preserving some of the structure of the polynomial kernel. 3. How PolynomialCountSketch works. 1. Hashing. The original features are hashed into a set of buckets. The hashing function used is based on random projections, which help to preserve the relevant information about the features. 2. Counting. For each bucket, the number of features that hash to that bucket is counted. This creates a sketch of the original features in the lower dimensional space. 3. Polynomial feature approximation. The CountSketch is then used to approximate the polynomial features. This is done by applying a polynomial function to the counts in each bucket. 4. Key values in PolynomialCountSketch. Let's analyze the YAML keys and their corresponding values within the context of a PolynomialCountSketch class. YAML. Gamma 1.0. Degree 2. N components 100. Random state none. Include appears true. Gamma. This parameter controls the scaling of the input features. It is essentially a regularizer that affects how much the polynomial features are influenced by a original features. A higher value of gamma results in more influence from the original features. Degree. This parameter specifies the degree of the polynomial kernel. A higher degree leads to a more complex and potentially more expressive model. N components. This parameter controls the dimensionality of the reduced feature space. A higher value of N components results in a larger approximation, which can be more accurate but also computationally more expensive. Random state. This parameter sets the seed for the random number generator used in the hashing process. It allows you to reproduce the results of the approximation. Include bias. This parameter determines whether a constant bias term should be included in a approximated features. This can sometimes improve the model's performance. 5. Applications and advantages. Kernel methods in high-dimensional spaces. PolynomialCountSketch enables the application of kernel methods like support vector machines to large datasets with high-dimensional feature spaces without encountering computational bottlenecks. Nonlinear feature learning. It provides a mechanism for automatically learning nonlinear feature representations from data. Dimensionality reduction. By reducing the dimensionality of the feature space, PolynomialCountSketch can improve model efficiency and reduce the risk of overfitting. 6. Limitations. Approximation. The technique is an approximation meaning it may not perfectly capture the information contained in the original polynomial kernel. The accuracy of the approximation is influenced by factors like the choice of n components and degree. Hyperparameter tuning, selecting appropriate values for the hyperparameters like gamma, degree, and n components requires experimentation and validation to ensure good performance. 7. Practical example. Python. From sklearn, kernel approximation, import PolynomialCountSketch. From sklearn, datasets, import load iris. Load the iris dataset. Iris load iris. X iris. Data. Y iris. Target. Create a PolynomialCountSketch object. PolynomialCountSketch. PolynomialCountSketch gamma 1.0. Degree 2. N components 100. Random state 42. Transform the data using the approximation. X transformed PolynomialCountSketch. Fit transform X. Now, X transformed contains the approximated polynomial features. Use these features for your machine learning model. 8. Conclusion. PolynomialCountSketch is a valuable tool for efficiently approximating polynomial kernels in high-dimensional data. By leveraging hashing and counting techniques, it allows for the use of kernel methods with reduced computational cost and memory requirements. However, it's important to be aware of the inherent approximation nature of the method and to carefully select the hyperparameters for optimal performance.